feel free to interrupt whenever you want. This is just summarizing where we've got to. Today we're going to get into the business of, pretty much before this, we've talked about atoms being embedded in a hot plasma, and some of the energy of the plasma is used to energize the atoms and their internal structure. And we've looked at the emission that comes as a result from those things that tell us, say, you know, look, here's a magnesium line, here's a silicon line. And we've gone over the basic ideas in a qualitative way. And what we haven't done yet, though, is acknowledge that in astronomy, there are generally speaking very large plasmas. And even if they're relatively tenuous, not very dense, you know, the product of the integrated mass through, say, a cloud or a corona or a chromosphere or something, and times the cross sections for the probabilities that a photon will interact with these things. You know, when they become bigger than one, then you have to deal with something called rate of transfer. And so today, I'm just going to give you a feeling for what rate of transfer is about. And we may end up being able to understand the formation of one of the strongest lines in the spectrum for the sun, notably the calcium-2 lines. And so we may or may not get that far, but let's just, and again, as usual, what I'll try to do is highlight the physical things as opposed to anything really mathematical. There will be some maths, there sort of has to be, because we're solving, at least in this case, ordinary differential equations, but it's not going to be horrific and it's going to be pictorial. So why do we need the need for some understanding of rate of transfer, and what is there anything special about it? Well, there isn't really anything special about rate of transfer. It's a subset of transport that you could model using the Boltzmann transport equation for particles, if you liked. And in fact, you know, it's possible. I'm just going to use the conservation of energy along a ray to define the transfer equation, which is a higher order, a lower order thing than the Boltzmann equation. The Boltzmann equation deals with phase space, and it means that for photons, you would have to track both the position and the momentum of the photon inside each 3D volume of space. The distribution function for photons, it has an H or an H bar in it because photons are quanta, and quantum mechanics, every time you see an H bar, you know there's some quantum mechanics in it. Or an A0 for a Bohr radius, or a Rydberg, or something, anything related to Planck's constant. And so, you know, obviously the Boltzmann equation looks a bit different from the transfer equation because we don't have acceleration of photons. They are themselves the carriers of forces, the electromagnetic force, not the they're not a massive particle. And so the transfer equation basically is just a subset of what we would normally expect if we had say an engineering degree and we looked at the particle transport and we looked at the hydrodynamic equations derived from integrating up those equations over various powers of momentum. Then we'd end up with like a Navier-Stokes equation or something like that. So it's really all part of the same thing. So our goal, of course, at the beginning of this whole thing was to extract from sets of measurements, whatever they may be, sets of physical parameters. So, you know, do we want to know the plasma density for some reason? Do we want to know the velocities of the plasmas? Meaning not necessarily separated out from the temperatures. The temperatures are just the random motions of thermal motion inside the plasma. And the velocities, by that I mean the bulk velocities, things like turbulence and fluids. We might want to know the elemental abundances. We might want to know the magnetic and electric fields. And if you look at what HAO does, you know, this looks an awful lot like a lot of what HAO does, except that in beginning in the Well, the story goes back to the 1960s, I guess, with spectropolarimetry. But the advanced Stokes polarimeter was one of the first really convincing instruments to measure the polarization state of the light as well. So as we know, we can look at photons or we can look at electromagnetic waves. It's two different ways of looking at the same thing, and they're glued together by the Planck constant, so that if you have a perfect knowledge of momentum, you don't know where it is, it's an infinitely long wave. If you have perfect knowledge of the position, then you have no idea what the momentum is, etc., etc. But we do know that in classical mechanics, the electromagnetic waves, they have a wave vector k, and perpendicular to this, you have a wave vector. You have an electric vector E and a magnetic vector B, and these form an orthogonal set. And the radiation propagates along the vector k, and the relative phases between and the amplitudes of the E vector projected onto the plane perpendicular to the propagation direction. So again, we're looking at the electric field and the magnetic field in the plane perpendicular direction. Those are, when you measure a stream of photons or of any kind of, represented also in your own, however you want to think of it, as an electromagnetic wave, then the polarization is a way of getting information about the behavior of the electric vector as it's propagating through space. And sometimes these electric vectors, when you have asymmetries and when you have external fields, these get to be asymmetric, and this is what HAO is very much about. And things like CMEX, of course, are designed to measure the magnetic fields, and in that case, we also have to worry about anisotropic processes, because when we're looking high in the atmosphere of the sun, we have no radiation coming down from the corona virtually, but we have a lot of radiation coming from beneath, which means it's asymmetric. So that's just a general introduction. And then the other reason to understand some rate of transfer is that in this big plasma, photons may have a very large mean free path. So, for example, in the corona, an ion of 171 angstrom, a line at 171 angstrom of ion 9, ion 10, it wouldn't interact very much with the plasma at all. All that would happen is the photons go into 4 pi steradians. Half of them go up, half of them go down. If they go down at 171 angstrom, they're going to photoionize something like hydrogen, and then the photon will disappear and it will release an electron. If they come out, then we can observe them with our instruments, and that's what many people do. For instance, the GOES satellite, SDO, they measure this radiation. But now consider something like, if you go deeper in the atmosphere, remember it's stratified as we get to the chromosphere. It's much like our atmosphere. If you try to shine UV light down into our atmosphere, you're going to get down, depending on the wavelength, you're going to get down only to a few hundred kilometers. Maybe you'll get down as far as 50 kilometers. But thank goodness for the ozone, because then we can't really get a whole lot deeper into the troposphere where we live. So the dangerous UV can't get down there. The same thing is true in the sun. The atmosphere of the sun is just defined as the place where the photons escape. And so if again we just imagine that UV photon going down from the corona towards the atmosphere, the deeper atmosphere, you have an exponential increase in the density every 100 kilometers. Eventually, it's going to hit a regime where the probability of it not interacting with the plasma is nil anymore. And at that point, then you say the photon has definitely been absorbed in some kind of structure inside the lower atmosphere. So we have to do rate of transfer because we've got to take care of that extinction effect, that e to the minus tau effect, okay? Again, this is very simple. There is one thing that's not very often highlighted, and that is that when we when we define a beam of light, we talk about the amount of radiation. The intensity is something I'm going to talk about here, which is the amount of radiation crossing a unit area, as at your detector or anywhere in space, and then per unit frequency nu, per unit time, but the d omega is the per unit solid angle. So what that means is the solid angle just defines sort of the momentum vector of where the photons are coming from, if you like, or it defines the solid angle from which you're viewing the sun. So, for instance, the amount of energy on the left, dE, if we had the Planck function of the sun in I nu, so we'd write I nu equals B nu of about 5,500 K, then we would integrate for dt, we'd integrate over all frequencies, we'd integrate over our detector area, but we'd also have to integrate over the disk of the sun as seen from our detector, and that's what the solid angle is. Now, if you think of it, dA and d omega cannot be made arbitrarily small in quantum mechanics, and the clue for that is that dA is a physical scale, and d omega is a measure of the directed momentum coming from that's defined coming from the source. So dA d omega essentially, if I write down from the Heisenberg uncertainty principle, I can say that P delta x is greater than h bar, and you can see that this must affect the definition of dE above, because dA d omega cannot be made arbitrarily small, and that's quite easy to see in the next equation. So we have something that says if we have an area and a solid angle that's too big, then we can't really use ray theory anymore. Forget the iconal thing. I can't remember what I wrote that for at this point. It's been a few months. But the rays we think of are curves tangential to the wave vector k. So it's saying that we don't really quite know where the photons are coming from when that inequality is done. But that's not a problem in optical physics, because even if you put in 0.1 arc second for d omega, the area of the detector is very large and the wavelength of the light is rather small. So, but it's just a thing to note, and the book by Rybik and Lightman is a very nice introduction to astronomical radiative processes. So unlike, say, the Boltzmann equation, so what is the Boltzmann equation? It says the rate of change of the density in phase space, the distribution function, has two what we call sort of macroscopic. Well, it has two differential terms in it. One says, how does the distribution function change in space along a certain direction? And the other one says, how does the distribution function change in momentum along a certain direction? Now, in rate of transfer, I'm gonna avoid the difficulty of knowing I mean, obviously the second term is zero, as I said, because we've got photons which are massless. So there's no acceleration term, and instead we can appeal to conservation of energy, which is built into Boltzmann's equation automatically, and we end up with a phenomenological transport equation, which is almost what everybody uses. And so this is where it starts not to look like electromagnetism or quantum mechanics, but it is electromagnetism and quantum mechanics. It's just it's just a notational difference. So, and by defining the specific intensity as we did up here, we can write down immediately along any direction S, along a straight line S, we have the change in the intensity is given by, defined by this on the left, is equal just to source term. So what are we talking about here? In the Boltzmann equation, we don't have a source term for particles on the right-hand side of the equation in the same way, unless we had nuclear fusion, and redshift transfer does have some analogy to the transport of neutrons in nuclear reactors. But what we have instead is we have the plasma. So J nu is just the amount of radiation emitted between S and S plus ds in suitable units as defined by this thing. Here's the amount of energy going in. And I've given you some of the nuts and bolts as to what this is. This is basically like Ni times some function of temperature if we have a plasma with the densities N electrons and ions and temperature, say. So this would say that the just conservation of energy, but then we have to take into account that every every length has with it an extinction coefficient, meaning that for a given energy put in, I take out a certain fraction of it in propagating through the plasma if I know what the absorption coefficient is. And the absorption coefficient clearly has units of 1 over length. Okay, so let me just rearrange things here, and I'm going to define so you're just completing the differential here. We have this term, and now if I divide by the absorption coefficient, this is sort of 1 over length. So this is 1 over length. So this number actually is a description of this number quantitatively is 1 over the mean free path at frequency S, frequency nu, at this position, central position S here. And we end up with an equation that looks like this. This is a very simple equation in principle. And if we now say, well, let's look down on an atmosphere and measure, instead of measuring height, S, coming through the plasma, let's measure depth going down, and let's look at it at an angle cos theta from the vertical. And then you end up with a standard form of the redshift transfer equation, which is given at the bottom here. I mean, what could be simpler here? This is for me was high school, maths. Once you know what S is, then for each mu, each angle that you're looking at, you can compute the change in the intensity. And if you have boundary conditions deep in the atmosphere and way the hell up above the atmosphere, then this in principle is solved. So what's the big deal? Well, the big deal is that in many situations, S cannot be pre-specified. So S, what is it? It's the ratio of the emission to the absorption. So if I now use the definition of this thing as 1 over alpha as being the mean free path, I now can say that the source function, this S thing here, is the amount of emission integrated over 1 mean free path at frequency nu. That's all it is. And then this just describes a kind of differential between so if I could start, say, deep in the atmosphere, specify S, and then I could start integrating this up and get a number here. But I would need to know S. And the problem is that throughout a lot of astrophysics, we know that S must be some kind of function of the intensity. And that's because when we look at an astronomical object, we're looking at photons which are escaping from the object. That means there's an imbalance, because we know that many photons under thermal conditions are emitted into 4 pi steradians, but we know that a full 2 pi of them are coming out towards us. We've only got 2 pi going back down. So we have all the regions we see are basically asymmetric in terms of the distribution of intensity with angle, namely that deep in the interior of the sun, if you went to the sun's center, it's entirely spherically symmetric to a good approximation. And we would write down that it's no chance that the photon mean free paths are so small that we'd write down the source function is the Planck function. We could do it immediately. And then we got the situation we want. We have mu di d tau equals b nu, which is only a function of temperature and frequency. once you got that, that's fine. The problem is now we go to the atmosphere of the sun, you've got photons streaming out, and we've got nothing coming down to keep the source function up at the Planck function. In other words, we no longer have thermal equilibrium at all. Instead, what we have is perhaps we have an equilibrium state of the particles in the atmosphere, but the intensity is only loosely connected through these J and U alpha terms to the plasma. And that's expressed by saying that the source function is an implicit function of the I itself. Okay? And you can imagine if I wanted to solve this equation, if this is a function of I implicitly over the whole atmosphere, over all frequencies, I've got to integrate this S nu over all frequencies and all positions, or for each frequency, I've got to find S nu. So I have to integrate this over all positions in the atmosphere. I have to integrate I nu in order to get this thing. And then if there's diffusion of photons in frequency, I've got to do it over all space. So this simple looking equation turns out to be a nasty integral differential equation. This is an implicit function of the entire atmosphere in which we have I. Okay. So just a few notes about this, a little bit further what we're talking about. It turns out that the quantity that's relativistically invariant is the thing that's proportional to the photon distribution function, which is a statement of how many photons are there at frequency nu at position x with momentum p. Okay, and p is basically h over lambda for the wavelength. So p is basically nu in another form. Okay. I said that this thing is the mean free path, and J nu is in these units here. Again, it's in watts per cubic meter, so that's amount of power radiated per unit volume per hertz, and then per steradian as required by the definition of I in terms of E. So the equation transfer again is here, and I'm just reproducing it to make you feel a little bit more secure about this thing. And the S is basically this thing here. The first result we see here is that if we don't have any emission, or I beg your pardon. If we don't have a contribution to U di by d tau, if this thing is zero, sorry, no. What am I trying to say? Oh yeah. So if we look at this equation here, we say that if this is zero, so in other words, at the sun center, we've got fully symmetric thing, then I nu equals J nu over alpha nu, and it's got to equal to B because of detailed balance arguments and statistical equilibrium. Now, if there are no sinks or sources, by definition, this is zero and this is zero. So I is constant in space. Now, this is a thing that's quite simple, but people are used in astronomy to thinking about the radiation falling off with distance to the -2, right? Because that's the classical theory of radiation has a determinant in which it's accelerated dipoles, and those you just go through the mathematics and it comes out like gravity. Force on the mass is 1 over r squared, and then similarly here the energy transported by radiation is 1 over r squared. But this thing is constant in space, so this thing is different from the flux measured at the Earth. And in fact, one way to look at it is to ask yourself the question, I make a camera, I just imagine a simple camera with one lens, an image, and the moon. And I take a picture of the moon, and if I reverse those two things, I could be the moon taking a picture of the image, or I could be an image taking a picture of the moon. So this is completely symmetric in some sense. And so whatever the quantity is at the moon is the same quantity it is at the photographic plate or the detector. And that quantity is the intensity. So no matter how far the moon is away from you, you use the same exposure time. Okay? And so if you were in 1969 taking a picture of the astronauts on the moon in July, or of the moon itself from the ground, you would use the same exposure as Buzz Aldrin might have used to take a picture of his boots. That's the meaning of intensity, which is, I think, kind of nice. Let's now look at what happens if we fix S, and I think that will probably, I'll go through this and we'll get some insights rather quickly here. But we're going to assume that S is given. Somebody has given you an S. It could be some clever person like Mads Carlsen. It could be some clever person like Gene Averett. It could be whoever has given you an S. And your task is to solve that equation. We need the boundary conditions, and we need the equation of relative transfer, okay? We also need the number tau, which is the number of mean free paths down into the atmosphere at that frequency. Okay, so the solution then, we just put in an integrating factor in I. So we do d by d tau of I e to the minus tau nu, and that gives you an equation combining these terms here, and we end up with a solution that looks like this. And now I've dropped the mu because I'm going to assume that tau is on a certain simple scale. So I've incorporated the slant angle into this notationally, but not explicitly. So the solution can be written down immediately from high school physics, and it's the intensity at some place away from the source is basically just declines from the source exponentially away from it. It's pretty damned obvious it has to be like this, right? I mean, what else could it be? And so if we now set tau nu equals 0, then we got x minus t, and those brackets, those absolute ones go to 0. So we just simply have integral of s e to the minus t dt. And if we put the boundary conditions in, so that there's, for instance, no photons going down, and we got a Planck function coming up deep down, then we have the formal solution. One of the most interesting things is if you say, well, let's do a Taylor series of S and T. I'm entitled to do it. It may or may not be physical, but it turns out to be useful astronomy because this number B seems to be small enough that this approximation is going to give you some sensible kind of answers. If I had shock waves or something, this would be wrong. So what is this saying? This is just saying that as I go deeper into the atmosphere, the source function increases at frequency nu. That means the temperature increases with increasing nu, and that's sort of what the sun's atmosphere looks like. And I'll show you why that is in a moment. So what we see from that then is that the emergent intensity, this is tau equals 0. So this is kind of messy, but this is very simple. This is just saying how bright is the disk of the sun? Well, it's about the source function at one optical depth. So that's absolutely the first thing result in relative transfer that's worth remembering, but you have to remember that it can't be changing too much with depth, okay? Okay. So that means that if we were to observe the sun from the ground, we would say it's roughly S nu at tau equals 1. And if I were to tell you that tau equals 1 is a place where, from a lot of frequencies, not all of them by any means, but a few of them, where LTE is appropriate. In other words, the photons are escaping, but the densities are high enough to maintain the source of photons in a thermal equilibrium, in a local thermal equilibrium, thermodynamic equilibrium state. Then I would replace this with a Planck function. That would tell me that the intensity of the radiation of the sun is a Planck function coming from a region where tau equals 1. And if I also were to tell you that that's around 5,000 K, I've got an explanation for the solar spectrum right there. That's simple as that. Okay. So I'm going very slowly for some of you, I know. Now, there is a reason to look at some angular means. I mean, if I'm sitting in the middle of a plasma, I see the intensity coming from below, I see the intensity coming from above. I might want to know what the average number of photons streaming through me is in order to determine the source function, because it excites atoms, and so I need to know all the radiation coming from all directions. So I nu is the thing that's invariant in free space, but through a plasma, it's going to change. And we can define the angle mean intensity, J, H, K. It just goes on and on. You can have a series of things. And the equivalent of this guy for J, you just take moments of the transfer equation, and you end up, instead of with an exponential, because you've got an extra mu in here, it's not. Mu is cos theta. We end up with an exponential integral, E1. So this is like e to the minus tau over tau. So this is a slightly different version of this kernel, which led us to say that the intensity at the surface is the source function at tau equals 1. This is telling us, if we know this function here, this is telling us roughly what the mean intensity is, how much total number of photons are coming into and out of a region, plus the incident radiation, which is just an e to the minus tau nu term here. And so I can write this thing operationally, just like I can write I of tau is some integral of e to the minus tau on s. I can just rewrite all these things operationally, and I can write this as lambda times s. So if we're looking down into the sun, here's the surface of the sun here, and we have a source function that's doing something here, then all I've got to do mentally is to multiply this by that, integrate it, and I can come up with an idea of what J is. Okay. Now, we know the width of this thing is about e to the minus tau over tau for large values of tau, but what it means is the width of this thing is about, one optical depth here, right? So the bulk of the source function is gonna come from this thing, and depending on the optical depth, if tau is tiny, this means this is optically thin. Well, I still can use the same equation. It's just I'm now adding up all the emission along this line of sight, because this thing, e to the minus tau, is 1, roughly. So optically thin emission from the corona is just going to give us the integral of s along tau, which is nothing other than the conservation of energy, saying total number of photons we put into the corona is the same as we get out. There's another one called the phi operator, and we can write it in exactly the same way. So now, again, this is now the cos theta weighted version. And if you imagine looking down on the sun, cos theta is plus 1, and if we look horizontally, cos theta is 0, and if we look vertically, it's minus 1. So what we're doing is we're basically taking the difference between the outgoing radiation, this stuff, and the incoming radiation and the upgoing radiation to this point here. So this is a phi operator, and this sine term here comes from the cos theta change of sign. And so we see now that whatever, and this number now is nothing other than this flux thing I spoke about. Namely, it drops off as 1 over distance squared from the source. That's not evident here because we're looking at a narrow region at the surface of the star. But it shows you that we subtract the outgoing downcoming radiation from the incoming radiation, and that's what we need to get the total flux across a certain surface. Okay, so what we end up with here, to me, I think it's one of the most beautiful things you can do with analytic transfer. So we take moments of the transfer equations itself. So instead of just taking the integral of I, we take the integral of these, integrate over mu to various powers. Power 1 with the h by d tau, power 2 for this second one. And what it means is the following. So again, I is invariant in space. It gets contributions from S and I along a depth measured going downwards. Okay. What's this? This is the rate of change of the flux coming out from a region at a given point, tau in the atmosphere, and is basically J minus S. So it's what you'd expect. It's basically the emission minus the absorption once you've taken into account the fact that you've changed the sign. You're going, increasing tau is going downwards into the atmosphere. So let's think about this. About 120 years ago, Schwarzschild and Millman people suggested that Schwarzschild did, that the atmosphere of the sun, instead of being in convective equilibrium, what's that? That's just stating that the divergence of the convective flux is 0 for the atmosphere of the sun. It's a hypothesis on the energy equation to define the upper state of the sun's atmosphere. But let's assume that the convection's kind of died out. And that's a little bit evident to me because the granulation is subsonic at the surface. So it's not carrying the full-blown, amount of energy of the sun anymore. Radiation is escaping. And so Schwarzschild said, well, maybe it's in radiative equilibrium. What does that mean? It means that the amount of energy absorbed locally by radiation is the amount emitted. Okay, so it means that dH by d tau is 0. In other words, the amount of emission minus the amount of absorption is 0. And now we could set J minus S equal to 0. And that is, given that we know that J is lambda of S, we could do a full gray atmosphere, assume there's nothing in the atmosphere other than just fog, gray. And we could say, well, look, this is J is lambda S. So lambda S minus S is 0. I know the form of lambda S. Therefore, I know what a rate of equilibrium atmosphere looks like. So I know how to compute a rate of equilibrium atmosphere. We haven't even done anything yet with rate of transfer. It's just nice and simple. This one is slightly different. There is a closure problem, like in the Bogoliubov-Boltzmann, if you're familiar with that closure. A different kind of closure completely. There are no photon sinks or sources by photons colliding with each other in rate of transfer. It's just the material. And we consider two pots of energy, one in the photons, one in the plasma, and this is what we're doing. We're looking at the interaction between them. But in a case like this, what you see is that each time I take an angular variable, I end up with something that I don't know about here. So I take the first moment and I end up with an H in terms of J minus S. But what is an S? What is an H? Well, we take the next moment and we end up with dk by d tau equals H. Well, that doesn't help us because we've still got a K. However, there are certain clever tricks that one can use analytically, and these very bright guys 100 years ago made some simple hypotheses. The Eddington approximation is simply one which accounts for limb darkening. So we have the intensity as a function of mu is A plus B mu. That means that at this center is brighter than it is at the limb if B is a positive number. And if you assume that, and you can observe it on the sun and say, well, it doesn't look like A plus B nu, it looks like A plus B mu plus C mu squared or something. But you can observe it, and you can make it a hypothesis that this is the first thing. So just with the rate of equilibrium, and then with this one, we can now put in a third J here for H. So then I have an equation which looks like this. A third J by d tau squared, d2J by d tau equals J. Now I've got a full solution like I have here, but integrated over angle. And now I can end up with what's called an Milne-Eddington kind of atmosphere based upon some very simple assumptions. So I'm trying to point out why this might be helpful. Okay. let's look at what really happens here when we have various structures. So there's this lovely book by Kurganov, this elementary that is in the 60s, called Basic Methods in Transfer Theory and Neutron Diffusion or something. Okay. And it's got these lovely plots in it, and it's a very gentle introduction. But he talks in terms of operators here. Notice that I've gone from a differential equation approach, this one, which you can solve by finite differences, and there are solutions that people have come up with that get rid of parasitic solutions, exponentially increasing, etc. And so there's a way. But now, what I've done effectively by looking at this is looking at it from an integral operator point of view. And for me, this is a lot more intuitive. But for other people, it may not be. So I apologize if it's not for you. And so here are the differential equations, but here are the integral operators. So now what do we get if we have b equals 1? So we say, well, what does that mean? S equals b equals 1 is what's being plotted here. So he's assuming it's in LTE, so the Planck function. So here what we have is, we have like an oven, all right? And we've got a hole in the oven at the front, and deep down, we know that the source function in the oven is going to be a Planck function because we think that the temperature everywhere, we have a small aperture like a black body radiation thing. But now I apply the lambda operator to it, and I end up with an expression which goes down to exactly a half, okay? What that means is that at the surface, which is 0, the intensity of the radiation is exactly a half of the internal radiation. Well, that's just a statement that we don't have any radiation coming from above. We've got this thing, so it has to be a half. So that's the lambda operator. So let's do 1 plus something, right? And let's do 1 plus a half times t. Then if I solve for that one, I find it's not increasing very quickly enough so that it lies underneath this thing and photons are escaping, and it can't quite catch up with this thing deep down. So with this, and then alternately, if we have a steeper one with alpha equals 3, say, then, and again, these are very close to the surface, 1 tau, 1 tau, 1 tau there. Then what we have is we have an excess of absorption over emission here, right? J is bigger than S. So what we're doing is this deep part here is actually heating up this part here, okay? And now we get the Goldilocks one, and we find that if we put alpha as 1.5, we get lambda b. Notice radius of equilibrium 0, J minus S, lambda b minus b. This is what a radius of equilibrium atmosphere looks like. So it's very simple. You have the source function varies as some constant times 1 plus 1.5 tau. And that's pretty damn close to what we have in the sun. And I've done almost nothing here. I think it's just beautiful. Let's have a look at some other ones. So let's say we have something like a chromosphere or a corona. The temperature's hotter here. The Planck function goes z to the minus alpha t, alpha equals 1. What we see here is that if we had, so this defines the temperature of the atmosphere. This is increasing outwards from deep down. And this is now the mean intensity. And notice how the mean intensity is trying to keep up with the sources of radiation here, but it doesn't quite. And it falls below the half point again. Again, another simple example is if we put in, like a square Heaviside function, this is what it looks like. What's going on is that this source of radiation is leaking out. There's no source of radiation here, and it's being absorbed by some of the opacity that's here, the grayness of the atmosphere, The photons can't quite get out from here. And so what's happening is that, so if we were to try and say by observing what the structure of the sun's atmosphere is, we would have one number for a gray atmosphere, and we would conclude that, oh, well, look, we observed this thing at the surface, and we observed this thing at the surface. You know, what use is that? Because we can't tell the difference between this structure and that one. So we have almost no information about the atmosphere from observations. But what we have is, from an argument of radiative equilibrium, we have a structure here that we can bring to bear on it. And we could say, no, we look down to tau equals 1, and this is the actual temperature structure. So what we've done is we've augmented just, you know, we allow it to have any old source term. We don't know what we're dealing with. But if we now recognize that, if we now believe for physical reasons that it has a radiative equilibrium state, then we know it's going to have to look something like this. There's no way around it. Okay, I think I'll stop. I think I'll stop there because it's going to get a little involved in interpreting a source function under a case where the source function is not, where the opacity, where the optical depth scale has a strong dependence on frequency. Okay, and then we'll look at how various structures propagate to show us what they look like, and end with the calcium lines. And then after that, we will begin to discuss, in general terms, the departure from prescribing the source functions. So we want to solve simultaneously for the sources and sinks of radiation with the radiation field. So as illustrated in this little sketch at the bottom here, our plasma consists of two tanks of energy. One is in the photons, which are just flying around all over the place. And if the plasma is being continuously heated, it's at one temperature all the time, then this state is going to reach a statistical equilibrium. And our idea is to try and find, through the coupling of the J's and the alphas and the taus and the S's, what radiation field is consistent with that plasma. So we want to make these two things consistent. And that's what we'll get into next time a bit. And then I'll talk about a very ideal case that we've talked about before, which is a two-level atom, which is very instructive. And we'll go slowly enough so that what appear like, you know, this looks like nothing you'll find in a Boltzmann equation or any other transport equation, but it's all the same thing. It's all the same thing, except that photons only originate when they interact with matter, or, you know, so that we don't have, like in a transport equation for a fluid, you don't have collision terms on the right-hand side between particles that you're solving for. And then we'll talk about the scaling of redshift transfer and an explanation. These graphs will end up explaining this thing here, which is something that Scott, the instrument guy, was interested in finding out how that works. So that's where we will go next time, if we get time to go far enough on that. And I'll leave it at that, I think.
Thank you.
Thanks for listening, and